So in this video, we're going to look at an additional example of how you determine the internal forces inside a beam given a particular loading condition. So we have a 3-foot beam, which is subjected to a distributed force. It has a peak value of 1,200 newtons per meter at the point of connection of the wall, and that linearly tapers down to 0 across the 3-foot span. And what we're interested in doing is in finding the internal forces at point C, which is shown to be exactly at the halfway point of the beam. So if you remember, the way that we do this is we're actually going to take the beam and we're going to segment it at the point of interest. And we're actually going to add in our internal force model, which we talked about in the previous video, which consists of a normal force, which is perpendicular to the surface of the beam, a shearing force, which is parallel to the surface of the beam, and a bending moment. So just to, and I have the answers here on a slide, but just to show you how that would look, and unfortunately my .cam has died, as often happens in this case, unfortunately. But when I draw that segmentation, what will happen is the portion on the left, in addition to having those 3 unknowns that we just described that correspond to our internal force model, it will also have, so just to draw very quickly, we have a 1.5 meter beam, a 3 meter beam, and at the midpoint here, that's where we're interested in solving for the internal forces. It is 1.5 meters away. This beam is loaded by a distributed force which tapers from some maximum value down to 0. And it's actually supported here by being fastened to a wall in such a manner. If you look at the nature of that support, it not only will be able to provide a reaction which opposes horizontal translation, so you can't pull it out, you can't shift it up and down, but you also can't bend it. So this reaction, based upon the idea that it's bolted to the wall like that, is going to have 3 unknowns associated with it because it can oppose horizontal, vertical, and rotational loads that are subjected to or applied at that particular point. So what I'm interested in doing is finding the internal forces here. So if I basically segment the entire beam and draw a free body diagram, on the left portion, which goes from point A to point C, I'll have my reactions, and I'm not actually going to draw it in here, but we'll just say that there are 3 unknowns here. And I'm going to have all my internal forces, which are going to be, according to the sign convention that we introduced in the last video, the normal force, the shearing force, and the bending moment. And then I have this portion of the beam. And remember that this is also in addition to your reactions and your 3, so we have 3 unknowns here. We have 3 unknowns associated with the reaction, and we have our actual load that's present upon this part of the beam. And in addition, this beam also has some load. However, the key point is that we know, or we can describe the characteristics of the actual loading force. And in addition, it has the internal forces, which are going to satisfy Newton's third law, meaning that if the portion of the left has a normal force that goes to the right, the portion of the right will have a normal force that goes to the left. If the shearing force on the left goes down, the shearing force will go up. And if the bending moment on the left portion is counterclockwise, then this bending moment will be clockwise. So there are 3 unknowns associated with the internal force description in both cases. However, on this right side, there are only 3 unknowns. So this is actually going to be statically determinate from the start. So don't be tempted in this actual problem to think that you need to solve for the reactions of the wall, because you actually don't. In fact, the only little bit of complexity in this problem will be in how you take and replace the portion of the distributed load, which exists on the right side of this beam, with an equivalent force. And that's why your book is showing you this WC here. It's just saying that in order to model the distributed load acting upon the right side of the beam, we're going to need to determine what the height is kind of at that transition point. And it's probably not too surprising to you that if this is a linear taper from 1200 to 0, then halfway across the beam, it's going to be at 600 newtons per meter. There's a couple different ways you could do it. You could kind of argue it from a similar triangle point of view. In addition, you could actually write an equation for this linear taper, but hopefully everyone can see if it tapers to 0 from 1200 at the halfway point, it's at 600 newtons per meter. So that's actually what they're showing here. So just going back, if you were to draw your free body diagram and actually draw it nicely in this case, the distributed force, and this is point B, this is point C, we have our description of our internal forces, the normal force, which is perpendicular to the surface, the shearing force, which in my original thing, I should have wrote that as V right here. It's an ugly V. And then we have our bending moment. When we actually describe the distributed load, remember that it is going to taper from 600 newtons per meter down to 0 over a span of 1.5 meters, because this section of the beam is 1.5 meters long. So if you actually want to determine the magnitude of that, remember that technically we would integrate from 0 to 1.5 this density function, w of x dx. But the definite integral over that span is nothing more than the area under that curve. So it's just going to be, since it's triangular, 1/2 the height of the triangle, which is 600 newtons per meter, times the actual base. So if you do that, that's just going to be 300 times 1.5, which is going to be 450 newtons. So that is the magnitude of that distributed load if we replace it by a single equivalent load. And in addition, we will want to apply it at 2/3 of the way from the actual midpoint here. Remember that when you have a triangle like this, I should have said 1/3, sorry, it's 2/3 from the small end, 1/3 from the big end. You're going to apply it or replace it by an equivalent force that's 1/3 from the larger side of the base. So just drawing a little bit by hand to show you why they're actually doing what they're doing. This is nothing more than the area under the distributed portion, the portion of the distributed load that's actually subjected on the right side of the beam. Notice that it is 1.5 meters wide, so 1/3 of that from the fat end is going to be 0.5 meters. That's how they determined where to actually place this load relative to point C. And then we have something that's statically determinate, of course. And all that we will need to do is to enforce our 3 conditions of equilibrium. What we see is that in the y direction, clearly the shearing force, Vc, is just equal in magnitude to the portion of the distributed load that's on the right side. I think we already determined, looking over my calculations, that is 450. Just going to the actual solutions in the text here. Not surprising, that is 450. In addition, since there are no horizontal reactions or no horizontal applied loads in this case, the beam will not be in tension or compression. So this normal force, Nc, is just going to be 0, as we would expect. And then the tricky thing, a little bit, maybe if you haven't done this so far, is to actually determine what the bending moment is. And you would want to sum all of your moments about the actual point of segmentation. Notice that if you apply a counterclockwise positive convention, the equivalent load corresponding to the distributed force is going to induce a clockwise rotation. So it will be labeled with a negative. This is nothing more. This fancy 1/2 base times height term is just the magnitude of that load. This is the perpendicular distance of it from the point of segmentation. Notice that by sign convention, the bending moment MC is also shown in the clockwise direction, so it gets a negative as well. And when you solve for that, what you find is that MC has a magnitude of 225 newtons per meter. And all that this sign turning out to be negative shows you is that the assumed convention is not correct. It's actually tending to have an internal stress that's in the opposite direction. So hopefully that makes sense to you. These problems are pretty simple until you get kind of a hang of working with the nomenclature and the new terms. They might be a little confusing, but remember that if you have a beam and it's subjected to external forces and you want to find the internal forces at one single point, you just segment the beam into 2 parts. And if one of the parts is naturally statically determinate or has only 3 unknowns, since the internal forces have 3 unknowns associated with themselves, that means you're going to have no other unknowns you are able to solve. If not, you just want to solve for the reactions first. So the only reason in this problem that we could solve for the internal forces right away is if we dealt with the right side of the beam, there were no forces that we didn't know other than those internal forces.